Hello there. In this video, we are going to graph this function using the techniques we've learned from calculus. And we're going to follow the guidelines that I've talked about in a previous video. So make sure you check that out. And the first thing we're going to do is start with number one here, determine the domain of our function. All right, so here's our function. It's a polynomial divided by a polynomial. Polynomials are defined everywhere. And so the only place this could be undefined is where the denominator is equal to 0. So how are we going to determine this stuff? Well, let's factor everything. So that may take you several steps, but this is what you'll get once you factor everything out. Okay, so now we'll look to see where the denominator is equal to 0. And we can see that it happens at three different numbers. It happens at 0, 2, and -2. So there are three numbers where this is undefined, but it is defined for every other number. So we can say the domain is all real numbers except -2, 0, and +2. All right, for the next step, we're going to determine the x and y intercepts. All right, so I'm going to take the next step of simplifying this function a little bit first. Okay, so to simplify the function, we can cancel common factors. And you see there's a factor of x in the numerator and denominator. So if we cancel that out, we get this. Now I want to point out something very important, and that is that we simplified it to this form. Now notice if I were to look for the domain of this function at this point, I would get the wrong answer. I would miss the fact that the function's not defined at 0, because actually this is not equal to this when x is 0. This one is defined at 0, but this one's not. So to be precise about this, I should really write over here, provided x is not 0. Right? Because otherwise these aren't actually equal. But as long as x is not equal to 0, then they are equal. Now how did that happen? Well, it's because I canceled out a factor which is equal to 0 when x is 0. So I have eliminated that value that was making this thing undefined when I've simplified it. So you do have to be careful about that. So that's why whenever you look for the domain of definition of a function, do it before you cancel common factors. Okay, but we want to find the y-intercept, and to find the y-intercept, we just evaluate the function at 0. And when we evaluate the function at 0, we plug in 0 for x, and you see that, okay, now here we have to be careful again. If I plug 0 into this, I would get 0 as the answer. But this is not our function. Right? This is only, our function only equals this when x is not 0. When x is 0, we have to go back to here. And I see that when I plug in 0, the function is undefined. And so this is undefined. So there is no y-intercept. Okay, what about the x-intercept? Well, to find the x-intercept, we just solve r of x equals 0 for x. So we're setting this function equal to 0 and solving for x. Now, how could that happen? Well, that could only happen when the numerator is 0. The numerator is 0 when x equals 0. Okay, well, when x equals 0, this function's not equal to 0. It's undefined. We just said that over here. And so, actually, this has no solutions either. So there are no x-intercepts. What is the next step in our procedure here? It's to evaluate the limits at infinity and negative infinity to determine the end behavior of this function. All right, well, let's go ahead and do that. Well, before we do that, let me do one thing. As we learned in previous videos, to investigate the limits at infinity, it's useful to divide through by the highest power of x. So I'm going to divide through by x cubed. And when you do that, you see that some x's cancel, and so we end up with this. Okay, so what we're going to be thinking about is the limit as x goes to infinity of this expression. And what happens? Well, this term goes to 0, this term goes to 0, and so I get 0 over 1 minus 0. 0 divided by a non-zero number is 0, so I see the limit is 0. That is the same thing that would happen if I took the limit as x goes to negative infinity. That's not going to change these facts. So both the limit to positive infinity and negative infinity are the same value. And what this tells us, not only is this the end behavior, but it's also telling us that y equals 0 is a horizontal asymptote. Okay, let's see what the next step is. Determine whether the function has any vertical asymptotes. So we're looking for numbers a, such that when we approach a from the left or the right, the function goes to infinity or negative infinity. Okay, so what numbers could those be? Well, where could this expression here approach infinity or negative infinity? Well, it's when the denominator gets close to 0, right? So that could happen at 0, 2, or negative 2. So those are the values we have to check. So I'm going to look at those limits. Okay, so I can't just take these limits. Some of these limits aren't going to be defined at all unless I approach from the right or the left. So let's just approach from the right on these and see what happens. As I approach 0 from the right, well, notice that if x is not equal to 0, and when we take a limit, we're not actually equal to 0, we're just approaching 0, this is the same as this function, right? What is this thing going to when x approaches 0? Well, the denominator is going to negative 2 times 2, that's negative 4. The numerator is going to 0, and so the whole thing is going to 0. Notice that that is not equal to infinity or negative infinity, so that means that it looks like this is not an asymptote. However, to be sure, we also have to check the limit from the left. However, if you take the limit from the left, you'll see the same thing happens. The numerator is going to 0, denominator is going to negative 4, and so the whole thing is going to 0. Okay, so no asymptote there. Okay, let's look down here. The limit as x approaches 2 from the right. Okay, well, again, if x is not 0, we're away from 0. We're near 2, so we can use this expression. Okay, so as x approaches 2, the numerator is going to 2. This term's going to 0, and notice that it's always positive, right? Because x is to the right of 2. We're approaching from the right. This term's going to 4. Okay, so this is going to 0 times 4. The denominator is going to 0, the numerator is going to 2, so the expression is going to infinity. This term is always positive, this is positive, and this is positive, so it's going to positive infinity. So this means that x equals 2 is a vertical asymptote. Okay, let's also investigate the limit as we approach 2 from the left, because we don't need to know that 2 is an asymptote. We already determined it, but it might help us graph the function later. Now, if I approach 2 from the left, that means that x is less than 2. That means that this term is now negative. But everything else is the same as we had before. So now we have positive divided by negative times positive, so the whole thing is negative. But it's the same basic behavior. It's going to infinity because the denominator is going to 0. And so, but we're going to negative infinity now. Okay, let's go down to the limit as x approaches negative 2. Negative 2 from the right. This term is, x is near negative 2, so this is near negative 4. This is, since x is greater than negative 2, this is positive, and the numerator is negative. So negative divided by a negative times a positive, the result is positive. And so this is going to positive infinity. It's going to infinity because the denominator is going to 0, right? Because this term is going to 0. So this tells us that x equals negative 2 is a vertical asymptote. But let's investigate the limit from the left as well to help us graph it later on. Okay, so we're approaching negative 2, but we're less than negative 2. All right, so this is approaching negative 4. This is approaching 0, but we're less than negative 2, so this is negative. So we have a negative times a negative, and the numerator is negative. So a negative divided by a negative times a negative is negative. So, and because the denominator is going to 0, it's going to infinity, it's going to negative infinity. Okay, let's see what's next here. We're going to compute the derivative of our function, find the critical numbers, and determine the intervals where f is increasing and decreasing. And then maybe we can find the local extrema, if there are any. All right, so I'm going to leave it as an exercise to you to compute the derivatives, the first derivative of this function. I'm just going to write down what the answer is here. Okay, so there we have the derivative. Okay, so we want to find the critical numbers. That's where the derivative is equal to 0 or undefined. Actually, maybe what I'm going to do is factor out this negative sign. Yeah, I like that a little bit better. Okay, so where can this thing be 0? Well, the numerator, notice it's never 0 because it's a number squared plus 4, so that's never equal to 0. But the denominator is equal to 0 at plus or minus 2. And so that's where this function is undefined, so those are critical numbers. And what that allows us to do is split up the number line into 3 different intervals. And actually, I noticed I forgot something. There's one more critical number, and it's 0. Why is that a critical number? Well, because if the original function's not defined at 0, then the derivative can't be defined at 0. So this is another place where the derivative is not defined. So let's include that. Okay, so we're going to be looking for the sign of r prime. When is it positive? When is it negative? Well, if I go over here to the right of 2, let's look at the value of r prime. Well, let's see. The numerator is always positive, right, because it's something squared plus 4. If I'm to the right of 2, I'm greater than 2, then this quantity, well, wait a minute, this whole thing's squared. This is always non-negative. So I have a non-negative quantity divided by a non-negative quantity, that's always non-negative. But then I have a negative sign on the outside, so that makes it negative. So notice that no matter what value x is, this thing is always negative, because it's negative, positive divided by positive. So negative, 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 negative. Wow, okay. What this tells us is that the function is decreasing everywhere it's defined. We can also tell from this that the function has no local maxes or mins, because remember, to have a local max or min, you have to have a point on the graph where the function changes from increasing to decreasing. That never happens. So we have no local maxes or local mins. Let's go to the last step. That is step number 6. It says to calculate the second derivative and determine the intervals where the function is concave up and where it's concave down, see if we can find inflection points. And we can try to use the second derivative test to find local extrema. But we know we're not going to find any because we know there aren't any from the first derivative test that we did up here. Okay, so I'm not going to go through the steps of computing the second derivative. I'll leave that work to you, so you should pause the video, work that out, and then check your answer with me. But here's what I got. Okay, so we're going to try to use this to find the intervals of concavity. So we're going to have to think about where this is positive or negative, and it can change from positive to negative where it is 0 or undefined, right? Well, okay, so let's see, where can it be 0? Well, that's where the numerator is 0. Well, okay, if x is 0, then the numerator is 0. There's no way this can ever be 0 because it's something squared plus 12. So, okay, one value is 0. So on the number line, I'm going to plot 0. What are values of x where this thing is undefined? Well, that's where the denominator is 0. Well, that happens at x equal plus or minus 2. So those are other places where it can change sign. So we're going to look at the sign of r prime. Where is it positive? Where is it negative? Okay, well, let's see here. If I'm to the right of 2, if x is greater than 2, this is positive. In fact, this is positive. It's never going to influence the sign of the expression. I can just ignore this for all these computations. So just look at the rest. The 2x, that's 2 times something positive. That's positive. If x is greater than 2, this whole thing will be positive. So the whole thing is positive. Okay, what if x is between 0 and 2? Well, this is positive, but this will be negative. So positive divided by negative is negative. What if x is between -2 and 0? Well, now this is negative, so the whole thing is positive. What if x is less than -2? Well, this is negative, this will be positive, negative divided by positive is negative. So there we go. These are the signs of our double prime. So we can see the intervals of concavity. Our double prime r, rather, is concave down on the interval -infinity to -2, union 0 to 2, and it's concave up on the interval -2 to 0, union 2 to infinity. Now, what about inflection points? Do we have inflection points here? Well, inflection points are points on the graph where the function changes concavity. So you might say, well, hey, yeah, look, we got 3 inflection points. But now be careful. An inflection point is a point on the graph, so the function needs to be defined there. Is the function defined at -2? Well, no, it's not. We verified that early on. Is the function defined at 0 or 2? No, it's not defined there either. So none of these are points on the graph. None of them actually correspond to inflection points. And if you wanted to think about the second derivative test to find where where local maxes or mins are, you would look to where the derivative was equal to 0. Now, the derivative was never equal to 0. There were no such values. And so the second derivative test tells us nothing. There's nothing to check here. But we know from the first derivative test that there are no maxes or mins. Okay, so let's sketch a graph of our function. Notice that the function didn't have any x-intercepts or y-intercepts. So there's no immediate points we can plot. But we did make some notes here about the asymptotes of the function. We deduced that y equals 0 is an asymptote. So we know that this is an asymptote. Okay. And we also had some information about some limiting behavior here. When x approaches 0 from the right or the left, we know the function is approaching 0. So we know it's tending towards the point 0, 0. But it doesn't actually get there. It's not actually defined there. So we're actually going to have a hole in the graph right there. Okay, what else do we see here? As x approaches 2 and -2, oh, we went to infinity. So we have some vertical asymptotes. So those would be worth plotting. So we have some vertical asymptotes. And what is the behavior of the function at these vertical asymptotes? Well, we can see that as x approaches 2 from the right, it went to a positive infinity. So that means it's going up to positive infinity up here. And we know that it can't come down and cross the x-axis because that would give us an x-intercept, but we know it has no x-intercepts. And we know that this is a horizontal asymptote, and we saw that when x approaches infinity, the function approaches 0. So it must go like this. And we know that when x approaches 2 from the left, it goes to negative infinity. Okay, well, that means it's not going up here. It must be going down here. And we know that the function approaches 0 like this. Moreover, when x approaches -2 from the right, let's see what we had there. -2 from the right, it went to positive infinity. Okay, so it must go up to positive infinity. So it must go something like this. And then finally, when x approaches -2 from the left, it went to negative infinity. So as we come in from the left over here, it was going down to negative infinity. But we know that as we approached negative infinity, the function was going to 0. So we know that the function goes out like that. So this is a graph of our function. And we can also verify that it is obeying those other things that we saw, the decreasing. It's decreasing everywhere it's defined. Notice we see that. It's concave up to the right of 2, concave down between 0 and 2, concave up between -2 and 0, and concave down to the left of -2. So it verifies everything we saw. And the one important thing I really want to stress here is this hole in the graph. You know, I think it would be tempting to fill that in or draw the graph through there, especially if you looked at the simplified form of the function. Remember, we had this simplified form, and yes, this function is defined at 0, and it would have that dot filled in. But that's not our function. Remember, this is only equal to our original function when x is not 0. Our function was not defined at 0. And so we are not allowed to fill in this dot here. We have to leave an open circle.